So let's jump onto the topic. The topic is power quality. So means we introduce about power quality, then we specifically go to the harmonics. We are going to talk more on the standards, just not IEEE standards, both IEEE as well as IEC standards on harmonics. Then we will be having some simulations. Then when the harmonic is means not within the acceptable limit of IEEE standards or IEC standards, then how to size the filter. I mean today we are going to focus only the single tuned passive filter. So and again probably means broadly put it, power quality is a very big term. Sag, swell, under voltage, over voltage, interruptions, shutdowns, right, flicker, and of course the harmonics. So in that we are going to deal mostly with respect to simulations only about harmonics. In that harmonics, I mean when the harmonics exceeds, I means again with respect to the standard we are going to talk in detail only with respect to IEEE 509. And with that, if the harmonic exceeds, I means how to size a filter. That too means only the passive filter. You may be aware there are active filters and passive filters. So we are going to discuss only on the so I'll say passive filter. In that too, say it's a single tuned filter. That's what I means, aiming at only one particular frequency to suppress that particular harmonics is what we are aiming today. So let's quickly click on this or play this. This you might have seen sometimes. If you want to better understand what is harmonics, I think this could help you a lot. All right, so first one, what you are seeing is a big circle with a radius of r. So when it is circulating, what to say, then it is creating a pure sinusoidal wave. And probably when you have a third harmonics and the magnitude of that means a small circle, that is assume that is one third of your, that's what the 3 is below, correct? No, means generally means theoretically we write nth harmonic magnitude is 1 by n of the fundamental. That's not necessarily true, but yes, in absence of data you can make that assumption. So probably with that, what to say, if we are adding the fundamental wave with the third harmonics, how this waveform changes. This is an animation which is available probably in the most of the places. I'm just taking this animation to better understand how this wave shape of sinusoidal changes when means fundamental is added with the third harmonics. And if it is added with the third and fifth, how the harmonics changes waveforms. So this probably you can play with the right. And of course the seventh harmonics, you can see the changes in means how many times it's reaching its maximum values, how many times it's crossing zeros, etc. Yes, fine. Let me quickly go to another animation. So I'm just ending up my session quickly with purely on animations. This few of you have worked in the industry might be aware this dbups, right? So yep. So some animations, if it is a controlled rectifier, the waveforms, voltage and current, means input power factor. What is the input power factor which they are talking about? So means we need to really understand one important aspect of relationship between harmonics and power factor. That's the predominant topic which we need to discuss, but anyway we are not going to discuss much on that. There is some what is a video which is available on a YouTube channel called the Power Factor Correction 1 Part 1 and Power Factor Correction Part 2. There means what is it, we have discussed in much detail with the relationship with the power factor and harmonics. You can go and watch there probably after the sessions. So here a quick conclusion: the input power factor is poor. That's because of total harmonic distortion is more, right? Some other waveforms. So I will quickly go to the linear nonlinear loads. Yes, so you can see the waveform difference between 6 pulse rectifier, 12 pulse rectifier and PWM rectifier. And I think those who are working in the research and doing some optimizations in the converters and inverters or rectifiers, so probably you can be in touch with some industries like that. Means you can check what's the harmonic level which they have in today's commercially available product. Then starting from there might be a good option rather than simply slightly starting from some simulations, right? This is a quick comparison between 6 pulse rectifier. You can see what's the current wave shape of the 6 pulse rectifier, and the 12 pulse you can see that's definitely a bit enhanced compared to the 6 pulse, but still that has some harmonics. But if you look at pulse with the modulation rectifier, that's means almost you are getting a sinusoidal wave. But anyway, means these are all things means which we need to really look into, individual products and their harmonics levels, etc., right? So for that, maybe at the end of the session, I may come up with some different variable frequency drives or solar inverters. What's their harmonics levels, etc. from the industry. Right. So here a quick comparison: single phase, 3-phase, 6-pulse rectifier, 12-pulse rectifier, and PWM rectifier. What's the input power factor? And what's the input current total harmonic distortion, and what's the conversion efficiency? Yeah, that's probably means if you are looking for some real-time data, this is real-time data from the manufacturer, right? Okay. Means how this is what we are discussing actually, how this power factor is related to this harmonics. Okay, anyway, that's a big question. As I told, you can probably go back and watch our power factor correction part 1 video. Linear loads and non-linear loads, quick conclusion. Yeah, this is a linear load, a load which draws current which is similar to the voltage wave shape which is applied. That's a linear load. So all your RLC loads, resistance, inductance, capacitance, all are linear loads. They may be leading power factor or lagging power factor. Right, this is a pure inductance, so current lags the voltage by 90 degree. And non-linear loads, that load draws a current shape which is not same of the applied voltage. So that means any power electronic device or arc furnace, that's all are of non-linear loads. And how to calculate the power factor? So that's a question.
Good morning everyone, this is Sia Ramada from Power Projects. So the title of today's webinar is Power Quality Analysis. So coming to the overview of the session, so we are going to deal with what is power quality, what are the power quality issues, and in particular what are harmonics, one of the major power quality issue, and what are the causes for harmonics, and what are the effects of harmonics, and how are these harmonics measured, and when harmonics need to be mitigated, and how are these harmonics mitigated. Form of bus voltages at rated voltage and frequency. That is the waveform at all the buses, that is the bus voltages should be at its rated voltage and frequency, that is it should be free from deviations, voltage deviation or frequency deviation, and the waveform of the bus voltages should be sinusoidal in nature. It may be non-sinusoidal due to some of the disturbances, but maintaining a perfect sinusoidal waveform of the bus voltages and its unrated voltage and frequency is power quality. So, what are power quality problems? So, any problem associated with the voltage or current or frequency deviations, either it may be an voltage deviation or current deviation or frequency deviation that result in the misoperation or mal-operation of the equipment or result in the failure of the equipment, then it is called, then those are called power quality problems. So, any problem that disturb the quality of power or power quality problems. And these power quality problems are caused in two ways. One is a natural cause, either it is lightning strikes, it may be of a distribution failure, or it may be due to falling of trees or branches in a distribution feeder. During the storming conditions, this may happen. So all these are natural causes. So this is one of the causes of power quality problems. So the another one is due to the operation of load or transmission line. So operation in the sense, if we energize the transformer, it may cause some power quality problems. If we switch on the capacitor, capacitor switching may lead to some power quality problems. And then the use of power electronic loads may cause some power quality problems. And the usage of arc furnaces and induction heating systems are one of the causes of power quality problems. And switching on or off large loads, this definitely causes power quality issues. So all these are the causes of power quality problems due to the operation of load or transmission line. So what are these power quality problems? There are many power quality problems. Among this, the major power quality problems are transients, long duration voltage variations, interruption, voltage sag, voltage swell, flicker, or in other words we can say voltage fluctuation, and harmonics. So you can see the pictorial representation of these power quality problems. So this is nothing but interruption, this is voltage sag, this is voltage swell, and this is long duration variations, long duration voltage variations, and these are transients, either it may be impulsive transient or oscillatory transient. And next, harmonic distortion, and this one is a voltage fluctuation. So coming to transients, transients are nothing but the sudden change in the steady state condition of voltage or current or both. Okay, this is just a sudden change in the steady state condition of voltage or current, and either it may be impulsive transient or oscillatory transient, as I told earlier. If it is an impulsive transient, these are unidirectional in property, and these are characterized by the rise and decay times. Just these are characterized by their rise and decay times, and these are unidirectional in polarity. So
Let me quickly go on to this. So what's power quality? What are the power quality issues? Harmonics and causes. What are the effects of harmonics? How these harmonics are measured, and how this has to be mitigated. So this is the topic which C has planned. Okay. So what's power quality? Of course, maintaining a pure sinusoidal wave with a rated voltage, rated frequency, without any interruptions or increase in voltage or decrease in voltage or shutdown or interruption. That's a pure sinusoidal wave at 50 hertz at a rated voltage in India, or 60 hertz at different countries where they use a 60 hertz. So that's about power quality. So means what are the power quality issues that can occur in voltage, current, frequency, power everywhere. So power quality with respect to the voltage wave shape can change from pure sinusoidal to non-sinusoidal. The voltage magnitude can come down, or it can increase, and it can increase or decrease for a very short time, or it can increase or decrease for a longer time. So based on means what's the change and what's the duration of the change. This can be classified as many sag, swell, over voltage or under voltage. Similarly, means current, that also has means changing the shape when the load is a non-linear. I have shown some images. So when I have shown some images, you can see that the load which is drawing a current which is not the same shape of the voltage which is applied. That's the simple reason, because of power electronic devices which is there. So that's basically means power quality issues with respect to current. Again, this current can be a shape which is different from pure sinusoidal. And frequency deviations, again, of course, frequency can change it from its rated frequency because of whatever may be the interrupt, increase in generation or increase in demand, whatever it is. Power quality can be because of natural causes, or probably because of what we are adding. Mostly means when we talk about power quality issues, when we talk about harmonics, that harmonics is mostly because of the nonlinear loads what is added in the customer end. And of course, this harmonics also becomes a problem nowadays with respect to this electric vehicles which we are talking about, and of course the sources which we are talking about with respect to the solar, as well as solar inverters will inject harmonics to the systems. Wind energy conversion systems like type 3 and type 4 wind turbine generators injects the harmonics to the systems. These are all the power quality issues, and so let's talk about the harmonics. I think these are all some power quality problems which you might have studied it in the textbooks itself. There is an interruption in the power in the first phase. There is a sag, that is a reduction in voltage for a short time. Swell, that is a increase in voltage for a short durations. Long duration variations, so probably means there is a change in the voltage for a longer durations. And you can see the oscillatory transients, means this oscillatory transients also could be because of the lightning. So probably if there is a lightning which strikes, means that that is with a very high frequency, right? The time duration is means 8 per 50 microseconds, so on so on. So means you can have some interruptions, or you can have some over voltages for a very short durations. That's lightning and switching transients. And you can have a harmonics. That's what we are going to discuss deal totally today. And there could be some voltage fluctuations. Right, transients can be impulsive transients or oscillatory transients. The oscillatory transients will be there forever, that keeps oscillates. Impulse transients, you can see that has the unidirectional polarity, and it is the rise and it decays over a time. But oscillatory, that's the means bidirectional, it's both positive and negative. That are also the case, but means what it has both positive and negative. So under voltage, over voltage means what to say, again probably this all depends upon how do we rate this over voltage and under voltage. So generally means what to say, over voltage relays are available to protect against this over voltage, or you can have means what to say surge suppressors, surge arresters, etc. to prevent this over voltages. So I mean despite of that, if your voltage goes beyond say 120 percentage for 2 seconds, your over voltage relay will be able to isolate your system. Under voltage, so similarly if there is a reduction in voltage, I mean what to say, that causes a damage to your equipments. So in that case, probably below 80 percentage of the voltage for more than 2 seconds, then you might be having some interruption. I mean you might, your under voltage relay will pick up and isolate the system. There is some interruptions as we can see due to whatever may be the reasons, like auto reclosures. Means you will be having a means interruption momentarily in the power. SAT, that is a reduction in voltage. So probably means you can see the RMS value at the top and probably the sinusoidal wave at the means below image. So there is a reduction in RMS values for a few cycles. That is SAT. And swell is increase in voltage for a durations, and flicker. So probably means nowadays everybody is talking about the flickers also, especially for a wind farms. So means you may use some simulation software like Dixelant Power Factory for this analyzing these flickers. Right, harmonics, I think you have fundamental, you have means multiples of harmonics, then the waveform is distorted. So Fourier analysis, if we are aware, this Fourier transform basically converts any non-sinusoidal but periodic waveforms into summation of sinusoidals and cosinusoidals. Hence so means any periodic but non sinusoidal waveforms can be constructed as summation of sinusoidals and cosinusoidals. That becomes basically harmonics and even multiples of like second harmonic, third harmonic, etc. Right? Fine. So flow of harmonic current, that's predominantly from means what to say, your source is of your loads. Harmonic source is your loads, which you can see that's in this case with the powertronic device which I have indicated, the harmonic current. When it comes to the harmonic current with the multiple paths, it takes the least impedance path. So probably if you have means what to say, offering a low impedance path for that particular harmonic using a filter, then that harmonic current will flow through that filter, and hence the harmonic current flowing through the source will be reduced. That's what the passive filter technique. But yes, we will discuss something more on the modeling and simulation of this harmonics. So this fundamental current always flows from source to load, but harmonic current is vice versa. That's always flows from the load to the generating stations. Not necessarily generating stations, wherever it finds the least impedance path. Like here, if it comes the harmonic current, then it has two paths. One, it can go towards source, and it can go towards another parallel path which has a least impedance. In this case, that would be a filter as well. Yeah. So what do you mean by linear load and non-linear load? Any load which draws a current in the same wave shape of applied voltage is linear load, and a non-linear load which is drawing a current with a different wave shape than the applied voltage, that is basically non-linear load. So here you can see linear load, that is power factor can be easily classified as a cos pi, that is cosine angle between voltage and current. That's means what to say, we generally has to call that as a displacement power factor, but for a pure linear load means what to say, power factor can be defined as cosine angle between voltage and current, because only one pure sinusoidal voltage and one pure sinusoidal current. So they have means what to say, the angle between the voltage and current can be measured, and the cosine angle of that is basically power factor. So that's the linear load. Example of linear loads are pure RLC loads, resistance, inductance, and capacitance loads. That's all of linear loads. So I mean, the resistor, the current and voltage will be in the same phase. So the angle between voltage and current is zero. So the power factor is unity. Whereas if it's a pure inductive load or a capacitive load, here what's the image which you are seeing is a pure capacitive load. So the current leads the voltage by 90 degree. So hence what say, cosine angle between voltage and current is 90 degree. Cos of 90 it is 0. So the power factor is 0 lead. Why we call it the lead? The current leads the voltage by 90 degree. And if it is a pure inductive load, the current lags the voltage by 90 degree. So means it the power factor is again 0, but
it is zero lag, right? But for a non-linear loads, it's something different. Means what to say, non-linear, the same definition cannot be applied. So because the wave shape, probably I think you have seen some non-linear loads. Yep. So the wave shape is not purely sinusoidal, even if the applied voltage is purely sinusoidal. When the current is non-sinusoidal, as this, but it is periodic, this can be constructed as summation of sinusoidals and cosinusoidals. That's what we call it harmonics. So since harmonic present, you cannot define the power factor of cosine angle between voltage and current. So cosine angle between voltage and current is just a displacement power factor. So there should be a distortion factor which needs to be introduced to find out what's the true power factor, right? So these are some basics of it. And meantime, let me quickly go on to the simulation itself. So let me talk about harmonics. I'm taking a 50 hertz system, right? So let's quickly go on to the simulations. So let me have a source and a load. Means I'm modeling a transformer. I'm connecting a grid. So let's quickly go ahead with the simulations. So let me take 110 bar 11 kV transformer of maybe 25 MVA. Let me assume a typical impedance. I am taking a winding configuration of delta star. But fine. So let me run a load flow. From there we will start. Let me run a load flow. So means there is no load connected. So obviously 110 kV voltage will be 110 kV and 11 kV voltage will be 11 kV. Both are at 100%. And if I want to plot the results in kV, yes, that I can do. I am plotting the results in kV. So it is 110 kV and 11 kV. Unit is not visible. If you want, you can display the units. Yes. So since there is no, what to say, loads, the voltage is maintained at 110 kV in the grid and 11 kV at the low voltage side. The transformer is 25. So means this you need to understand that there is an industry which has about 15-20 megawatt load, which has 110 by 25 MVA transformer stepping down to 11 kV and feeding its loads, right? So we will try to introduce some variable frequency drives. Assume that that's a cement industry or a tire industry or a steel industry which has variable frequency drives, and probably we will also add some solar panels. Assume that that industry has some rooftop space at the land nearby, so where they are adding the solar panels. Then let's check, means what is the impact of this loads or the solar inverters or probably means wind turbine generators and its impact on the harmonics, right? So let's plot the angle as well. This is 110 kV, this is 11 kV. Let's plot the angle as well. So I can plot the angle with the voltage. So here you can see 110 angle 0, here it's 11 kV angle 0. But please always be remember, though its source is a 0, when a transformer is delta star grounded, definitely there could be a 30-degree phase shift which is introduced because of delta star. If you do not know why this 30-degree is introduced, I have to refer a standard IEC 60076. So you can go and refer that standard that tells, means what's the winding configuration and what's the phase shift, right? Delta star transformer definitely introduces a 30-degree phase shift at least. That could be either lag or lead. So then why still it is saying 0? Because I have made an assumption in a load flow that means what to say, the phase shift is not really necessary for my analysis. That's what I have assumed. So that's the reason it was 0. But now you can see, yes, when the grid is at 110 kV angle 0, means the LV voltage is 11 kV but at minus 30 degree. That's because of means what to say, the winding configuration what I have selected. I have selected DYN1. So that is HV leads LV by 30 degree. So now the results LV is minus 30 degree, that is lagging the HV by 30 degree. So the vice versa is also possible. Means what to say, I can go with the DYN11. In this case, your LV voltage leads the HV voltage by 30 degree. So probably means this is not the only configuration which is possible. Of course, you can go with the DYN3, DYN5, DYN7, all possible combinations, right? So it means how this vector group impacts our harmonics. That's also an important reason, because when there is a delta star transformer, that eliminates third and multiples of third harmonics. So that's the important point which I am trying to stress here. So that's also a real reason why I have taken in this delta star transformer. Okay, so means I have completed a load flow analysis without load. That's fine anyway. So let me run a harmonic analysis as well. So I'm just going to harmonic analysis. So let me plot both the bus results. I want to plot both the buses. Fine. And if it's a transformer, let plot transformer also. Right. Now if I run means a harmonic analysis, obviously there would be some error which is expected. So let me run to show that error, then I will come back to this what is that error. Yes, you can see the power grid 3-phase short circuit MVA is less than 0. That's the error which is saying. What is it? The load flow analysis can run even without specifying what is the short circuit level at the grid or what is the source impedance, because that's assumed as a slack bus and that voltage at bus 1 is referred as 1 angle 0. And that's not true for a harmonic analysis, because when there is a harmonic current which is injected by your loads, that has to flow through the sources, and that source impedance has a direct impact on your source short circuit level. So let me quickly take some short circuit level at the grid. So let me take 31.5 kiloamps as a short circuit current at 110 kV with an X by R ratio of 40. Let me run harmonic analysis now. So I am not displaying the units, so let me display the units as well. Yeah, total harmonic distortion is 0 for both voltage as well as the current. So here you can see 11 kV side the total harmonic distortion voltage is 0, 110 kV side also the total harmonic distortion voltage is 0, current 0 amps RMS and 0% THD, because I have not even added any loads, right? So since there is no load, there is no current, the voltages are at 1 per unit and the total harmonic distortion both voltage and current are 0. Now let me add a linear load. What is linear load? A linear load which draws a current at the same voltage shape, right? So let me take a load 1, that is a static load. I'm just taking a load of maybe say example 10 MVA. I'm taking at unity power factor, that's fine. Okay. So let me means what say why I am saying it's a linear. I mean when you say harmonics, there is no harmonics in the systems. So you can say means what say this load doesn't include any harmonics or introduce any harmonics. This is going to draw a pure sinusoidal current when the voltage applied is pure sinusoidal. Yes. So now let me run a load flow first before going for a harmonic analysis. I believe the screen is visible and the results are visible. So previously the voltage is about 11 kV. Now it has reduced to 10.97 kV. That's all because of means what say there is a loading on the transformer, right? Let me change the angle to DYN1 itself, right? Then the angle could be minus 32. What is this minus 32.28? So minus 30 by default introduced by this delta star transformer because of DYN1 what I have selected, and the additional 2.28 degree is the lagging angle, that's because of the power flow in the transformer, right? So that's a bit clear. So now with that background, let's move on to the harmonic analysis. So far what I have run is only a load flow analysis, right? So look at the power factor as well in a load flow analysis. What's the power factor now? I have given 10 MVA unity power factor load at LV, but it's actually it is not reflected as a unity power factor, it is reflected as 0.9992. The power factor is not unity. Why the power factor is not unity? The power factor is not unity because there is some real and reactive power losses in the transformer. So you can see there is a loss in the transformer. So I mean to say, though the load is not drawing any reactive power, the transformer is drawing a reactive power from the system, and hence the power factor is not unity. That's because of the reactive power loss in the transformer. Yes, so that's all probably true power factor as well as displacement power factor because the load is linear. Let me move on to the harmonic analysis. So let me run a harmonic analysis now. Yes, again total harmonic distortion is 0 because the load is linear, which is drawing a pure sinusoidal current. So 10.97 kV is the voltage, that's the same. Means you can see the current drawn from the HV side is 52.3, that is at 0% THD, and 110 kV it is at 0% THD. So that's the basically I mean so to say I have considered a pure linear load, so there is no harmonics at all. So let's introduce a harmonics. So the harmonic I am introducing by means of means what is some by default library which is available. So you can take any manufacturer and you can choose some model numbers. This is by default library which is available in the model, that is manufacturer ABB ACS 600 is um, basically the variable frequency drive, 6 pulse variable frequency drive, you can check. So if I'm just clicking OK to just to showcase how the waves form is, right, you can see this is so to say 6 pulse variable frequency drive from ABB, that is ACS 606P, that 6 pulse, and that so to say what's the current drawn by that particular 6 pulse VFD. If I'm changing that to say 12 pulse VFD, so here you can see some much better wave shape. So here the voltage waveform is purely almost close to sinusoidals. So you can really understand the difference between 6 pulse wave shape and 12 pulse wave shape, right? And here you can see so to say harmonics are of 11 and 13 are predominant. And let's quickly go to some pulse width modulation rectifier as well, PWM. Yeah, that's the probably you can check what's the so say current harmonics, etc. So probably that is the same story of what's the comparison which I have given somewhere here. Yep, sorry for moving fast. Yeah, so that's a quick comparison which you can probably relevant or relate to the same sheet. Right, done. So now so to say rather than going with some manufacturers, let me take a typical IEEE 6 pulse current source. Okay, so here you can see so to say the harmonic could be a current source or even a voltage source, right? Arc furnace is a typical example of voltage source harmonics. Okay, so now I am just taking a 6 pulse drive, that is of typical IEEE standard which I am using. That you can see so to say the wave shape is almost so it's like a square wave, right, with a huge harmonics. Let me run simulations and let me try to have a look at that, right? Yes, so to say there is an about 11.06 percentage voltage total harmonic distortion at your bus 2, that is at 11 kV, and the voltage total harmonic distortion is 0.431 percentage total harmonic distortion at bus 1. That's on the HV side, and your current harmonic is about 26.86 percentage. So now what are the results which you need to compare? Your voltage total harmonic distortion, voltage individual harmonic distortions, current total harmonic distortion, current individual harmonic distortions, all these 4 parameters with respect to IEEE 509 guidelines at point of coupling. So you need to understand what is point of common coupling, that is PCC, generally defined as PCC is the point at which where the responsibility of the utility ends and the industry starts. That's probably where you have a energy meter. So assume that this industry gets the power supply at 110 kV and the meter is available at 110 kV, then at 110 kV you need to check whether this data is within the limit or not. So if it is within the limit, then fine. If not, then you need to really size the filters to mitigate the harmonic impacts. So let's quickly talk about the standards available to talk about this harmonics. There are many standards from IEC, most specifically IEC 61000 series. So that talks about complete power quality, right? IEEE 509 is basically recommended practice and requirements for the harmonics control in electrical power systems. That's latest version is available from 2014. And IEEE standard 3002, which has came recently, also gives some practice for conducting harmonic studies and analysis for an industrial and commercial power system analysis. This replaces the famous IEEE color book series, and the latest IEEE standard 3000 series is talking about the recommended practice for harmonic studies. And this is the extract from the IEEE 509. So probably the previous IEEE version doesn't has splitted this less than 1 kV and less than 69 kV, but now that has been introduced in IEEE 509 2014. So if your voltage is less than 1 kV, individual harmonic distortion allowed is 5% and total harmonic distortion allowed is 8%. Please be remember this is VTHD, voltage THD. And from your point of common coupling voltage is 1 kV to 69 kV. This individual has to be 3 and total has to be 5. And 69 to 161, this is 1.5 individual harmonics and 2.5 total. And more than 161 kV, means it is 1% individuals and 1.5 total, right? So means for say a note that is some asterisks, that is high voltage systems can be up to 2% THD if there is a HVDC terminal. That means more than 161 kV you may be having means high voltage direct current HVDC stations. So the HVDC stations, I mean, so say it's allowed up to 2%, right? That's voltage harmonic distortion. So here it's an individual harmonic distortion. This is total, and here we so to say this is a current distortion limits. Current distortion limit is given based on ISC by IL. ISC is the short circuit level, short circuit strength of the system or that point of coupling. IL is your load current. So when your ISC by IL ratio is different, then the allowed ratio or rating is also different, right? So I mean, so to say, total demand distortion TDD. There is another pattern which is introduced that needs to be less than 5% at your point of coupling forever. Okay, and I mean, so to say, though there are many values are given, most of the times people tend to always compare the results with the first one, that is less than 20 ISC by IL, because I mean, so to say, proving what is the minimum short circuit level at point of common coupling might be extremely difficult from the customer perspective. So when this ISC by IL is less than 20, means if your harmonics from 3rd to 11th has to be limited to 4%, 11 to 17 to be limited to 2%, and so on, and total has to be limited, total demand distortion should be limited to 5%, right? So I mean, so let me look at whether this we are complaining or not. So I mean, the total harmonic distortion voltage is 0.431. That needs to be compared here. Means what is the voltage? We have an 110 kV common coupling voltage. So means we may fall on this category 3, that is 69 kV to 161 kV. So means what say, individual harmonic distortion should be limited to 1.5 and total harmonic distortion to be limited to 2.5. So here if you look at means total harmonic distortion is 0.431, and if you want to find out the individuals, you can find out this kV 177 divided by 11 kV you can put, and you can find out the values, or probably you can I mean, so it's display in percentage also, I believe, right? Yes, yeah. So fifth harmonic is 0.16 percentage, seventh is 0.156, and so on, right? So means what say, our total harmonic distortion is less than what's the standard requirements. So here means the standard says you can go up to 2.5 total harmonic distortion. So we have limited to 0.431. So the individuals it should be less than 3. The total itself 0.431. So obviously means what is it? The individual will be definitely less than 0.31. And if you want to look at the individuals, that I mean, so to say, is very small values 0.16, 0.156, 0.145. So it's all small numbers. So means what say, we do not have any constraints on the voltage distortion limits to meet the requirements of IEEE 519. So that's not the entire story. So let's look at the current. So current, the total harmonic distortion, this is THD, not TDD, total harmonic distortion. Okay. Anyway, this total harmonic distortion, what you look at, this is 26.86%, right? Means that you should not compare with the TDD, but you can look at means what is it, when the short circuit level divided by the full load current is less than 20, then you need to take the first one as a reference, and you need to most likely means you need to meet this, right? So with that, if you look at means what say, your total harmonic distortion is definitely too high, that is 26.86%. That's not means really acceptable. For that, you may need to means what say, size a filter to bring down this current harmonic distortion. So the conclusion is like means though the voltage harmonic distortion is within the limit, if the current harmonic distortion or current total demand distortion exceeds the limit, you need to go for a filter, right? So that's means what say, let's quickly check the wave shapes, how the wave shapes is, whether they are purely sinusoidal or not. So let's quickly check the waveform. Sorry, every time. Okay, let me look at only the waveform at bus 110 kV. Let me look at the waveform of bus 110 kV. It's almost pure sinusoidal. This is because the total harmonic distortion is 0.431 percentage. So it may, to your eyes, it may looks like it's a pure sinusoidal, but though it is not really a pure sinusoidal. But when you go to bus 2, then you can easily understand that's definitely not a sinusoidal. Yes, bus 2 is here. Now you can understand this is not definitely a sinusoidal. So that is because of the total harmonic distortion at bus 2 is 11.06 percentage. But you need not really worry about this to meet IEEE 509 requirements, because IEEE 509 requirements basically means what they talk about this total harmonic distortions at point of coupling. But now one interesting fact is the voltage wave shape is not purely sinusoidal at 11 kV bus. This wave shape you can see it's something it's very awkward. Okay. Now if I am adding an additional load at bus 2, assume that that's a pure linear load. Assume that's a pure linear load. Now that load also will try to draw a means what to say current which is of non-linear in nature. That means non-sinusoidal in nature. So let me plot the loads as well. Let me check whether I can plot the loads. Answer is no. So means what to say, in order to plot some values, let me introduce the cables. I am just trying to put up the cables for a better to display the results. Let me take 11 kV cable, maybe only with a few meters. That is just for displaying the results, nothing more. Let me take a 10 meter cable with the library of 240 square mm cable. That's anyway fine. Maybe assume 4 runs. Right. Now, so to say, this load is a non-linear load. Let me copy this and add an additional load. That's the pure linear load. Let's add a load. Assume the load 2 is purely linear. How can I say that load is a linear? I am making that there is no harmonic source which is available in load 2. So means the comparison or a difference between load 1 and load 2. Load 1 has harmonic source, whereas load 2 doesn't have any harmonic source. So that means load 2 is a pure linear load. Right, now let me go back to this harmonic analysis. Let me plot all the cables. Right, to understand means whether this linear load draws a linear current or non-linear current. So let me run a load from harmonic analysis now. Yep. So here there is an interesting fact, very interesting fact. The total harmonic distortion at your 11 kV came down. Correct? Now previously it is something more than 10%. Now it is 8.26. So here it is previously 0.431%. Now it is reduced to 0.322%. But let's say even your total harmonic distortion current in terms of percentage it came down. Okay, that's fine. But if you look at this a load which is a purely linear load, I haven't given any harmonics on that particular load. Still that loads draw a current which is of what to say non-sinusoidal in shape. How can I say that? What to say the load is non-sinusoidal. Sorry, the load is purely a linear load that's supposed to draw a pure sinusoidal current. That will draw pure sinusoidal current. Probably let me make this load out of service. Then I'll just show you. If you want to prove that, yes. Now I made this load out of service. That means a non-linear load I made it out of service. This is a pure linear load. The load 2 is a pure linear load. It is not drawing any harmonics. The current and voltage wave shape is purely sinusoidal. That's the reason why we are getting 0% THD. So assume that this is a linear load which is available, and you can check very well the voltage and current. I think I can delete this. Yes, I can probably plot the cable. That is, I believe, cable 2. Yes, cable 2. I can probably plot waveform. Yes, this current is lagging. That is because of the delta star transformer. Anyway, so here if you see, what to say the wave shape is purely sinusoidal. Now means this is a pure linear load which draws a pure sinusoidal current. But as soon as there is another non-linear load which is added in parallel with this load, then so to say this load is still so to say is a linear load, no doubt about that. But this linear load draws a current which is at the same wave shape of a voltage. Unfortunately, this voltage is not purely sinusoidal. If you look at the bus 2 voltage, the bus 2 voltage is not sinusoidal, and hence the current drawn by the load 2 also becomes non-sinusoidal. That results in some harmonic currents. So let's plot the bus 2 voltage. Bus 2 voltage is not sinusoidal, and hence the load which is connected to that bus 2, which is linear in nature, also trying to draw the same wave shape. So that's the reason why 8.26% voltage total harmonic distortion, the current drawn by the load, linear load, is also 8.26% current harmonic distortion. So means you need to understand the fact that even if your industry doesn't have any nonlinear loads, if the supplied voltage is not purely sinusoidal, then means what to say, you will be having a harmonic current. So that's probably the message which we need to really take into account. So that gives you an approximate idea of what's its impact. Okay, so now let's probably move on and discuss a bit more the impact of the source impedance. So now I have assumed my short circuit current at 110 kV is 31.5 kiloamps with an XBR of 14. With that, what's the total harmonic distortion which we have it in bus 1 is 0.322%, current harmonic is 11.86%. So let me take an Excel sheet to tabulate these values for an AC comparison. So bus 1, that is at 110 kV, and probably bus 2, that is probably 11 kV. So let's compare both voltage THD and current THD. So let me take voltage THD and ITHD. ITHD is not the current distortion, that is probably, let me put the THD suffix I, right? So that is current distortion. So bus 1, if you look at the voltage THD is 0.322, current harmonic distortion total is probably the incomer which you can take, that is 11.86, all are in percentage. If you look at bus 2, the voltage THD is 8.26, that's quite high. And if you want to measure the current harmonic distortion, you have to put a cable here and you have to measure, or probably that's what transformer, it either displays on the high voltage side or low voltage side. So you can put an additional cable and you can check what's that value. Anyway, that we are not much interested in. But this is with a short circuit level at a grid of 31.5 kiloamps. Right now, let me change the short circuit level from, say, example 31.5 kiloamps to, say, example merely 5 kiloamps. Right. So I am not changing any other parameters. I am just trying to change only one parameter, which is grid short circuit level. Let me change the grid short circuit level from 31.5 kiloamps to 5 kiloamps. Let me rerun my results. Yes. So now you got some difference. So what is that? Your total harmonic distortion voltage is increased to 1.87%. Your current distortion is 11.29. That is almost similar. And bus 2 voltage total harmonic distortion is 9.14%. So here is a big difference. So your grid short circuit strength has a direct impact on voltage total harmonic distortion at your point of coupling. So when the short circuit level come down from 31.5 kiloamps to 5 kiloamps, your voltage total harmonic distortion at point of coupling has increased from 0.322% to 1.87%. Now if you compare this with your acceptable limits, right, we fall in this category 69 to 161, right? It is 1.5 to 2.5, that is total. Individual has to be less than 1.5. So still total is within the limit, but you need to look at the individual has crossed 1.5 or not, right? Luckily it is less, luckily it is less, so still you are in a safe, right? So means what to say, still the total harmonic distortion voltage has increased, but still it is within the IEEE 509 limits. Now let's what to say, just changed the short circuit current maybe further to say example 2 kilams at 10 kV. Then you can see your total harmonic distortion is 4.05 percentage. That is the results with the here you can see the total harmonic distortion is 4.05. That is definitely not within the limit of your IEEE 509, right? Where your means what to say, harmonic distortion is quite high, and that is definitely more than IEEE 509 limits. That means you are just not meeting the current distortion, but also the voltage harmonic distortions, both the total and might be individual as well. That individual you need to check whether the individuals are less than 1.5 percentage or not. Yeah, probably you can see fifth harmonic distortion is 2.13 percentage, which is higher than what is the acceptable limit of 1.5 percentage. So did you have what say everywhere exceeded the limits, then obviously this means there is a filter which is really mandatory, right? So what say this is a quick comparison of what say I have added a non-linear load, I have added a linear load, and I have shown some differences, etc., right? So now let's also quickly add one more important harmonic source in electrical power systems. That could be your UPS, your variable frequency drive, your chargers, your inverters. So means if you take any of these equipments, that means this all the equipments has power drawing devices in it. So if you take any of these equipments, then that will be having harmonics, right? So let me quickly model the variable frequency drive. So let me draw a direct drive. That means that's directly connected at 11 kV with a motor. Anyway, for a simplicity, I am not drawing really the loads which needs to be, means the cables which needs to be connected between this. So let me take a 4000 kilowatt motor at 11 kV. The bus voltage is 11 kV. The variable frequency drive should be, what to say, output should be higher than your motor input. So I might be giving say 4300 kilowatt, right? So input power factor can be 100, but efficiency say example 94, right? That gives the input kV of that variable frequency drive. Now if you look at this harmonics is obviously a variable frequency drive. I am trying to model ABB ACS 600 or Rockwell 6 pulse VFD. These are all the same variable frequency drives which is modeled as per the manufacturers. And if you have some other variable frequency drive which is, if it is not available in ETAP, you can develop your own library, and you can even write IEEE 509 equations to find out what's the harmonic levels, right? And if you want to include interharmonics, that you can include. So you may be talking about interharmonics and intraharmonics. So we are now talking about the harmonics which are multiples of fundamental frequency, and you can have also the harmonics which are all what say not necessarily the integer multiples, but in between as well, right? So I have added a variable frequency drive. So this variable frequency drive also injects some harmonics to the system. So let me go back to run a harmonic analysis, right? So here I don't think it is what say it's not contributing. It's contributing, but it is not really displayed it. So let me add the same cable of what's available here as a cable 2. Let me add a cable 3. Yes, and probably let me go to the harmonic analysis and let that harmonic analysis let me plot the cable 3 as well, right? Yes, so you can see what say your system, your variable frequency drive injects about a 25 percentage total harmonic distortion. So that's huge, and hence that will be having an impact on your total harmonic distortion at voltage as well as your both current voltage at your point of coupling and all the voltages. So that's just an very example. I mean, so say here means I have just simply modeled the loads. I have added a harmonics, but in a reality means what to say the system like this, the variable frequency drives, the loads which injects the harmonics to the systems are like UPS, variable frequency drives, inverters, chargers, rectifiers. All these power electronic devices will inject harmonics to the system. And even your solar inverters, if you take the solar inverters injects the harmonics to the systems. So I mean when you are adding a wind turbine generator or solar inverter, either it's a grid connected systems or probably means what you say you have this some uh, sorry. Anyway, one of my questions has I mean collected some questions. So I mean I will go through the questions one by one, and probably means also let me take up other questions probably when time permits. The Nagaraju, can anyone post the IEEE standard for power quality? I think that I have told, means that's what we have discussed, IEEE 509. And what's the voltage level frequencies THD limit? I think to answer Nagaraju question, so we have given the limit of IEEE 509, both voltage, current, everything. That's what you can see here. And Deepak, power sim simulator, good enough to do this simulation, sir? So answer yes. I mean, so say ETAP is not the only software which is available to perform harmonic analysis. There are many softwares which are available, but I generally suggest you to use power system simulation software. That means the simulation software which is used for power system studies, like ETAP or Excel and Power Factory, etc. Simple reason because you will be able to model. I mean, the entire power systems, including transformers, cables, variable frequency drives, inverters, etc. So that has an advantage over specific simulation software. So means you need to really understand one important aspect. When you want to perform a this power quality analysis or a specifically harmonic analysis for an industry or a solar plant, then it is advisable to go with the kind of simulation software like ETAP or Excel and Power Factory. But if we are more specific with respect to some product, like means if you want to test only the inverter, if you want to test only the converter, if you want to check only one particular variable frequency drive, then it is better to go with which would say some softwares like even MATLAB that helps you, because there you are means what to say trying to find out or control some parameters, or you are trying to write some algorithms to control the harmonics of that particular device. Here means what to say you cannot have any control over what's the harmonic injected by the devices. That we need to give us an input. So this softwares like ETAP or Excel and Power Factory, these are all used for overall systems where there are many harmonic sources. Where you are trying to find out or optimize your converters or inverters, then probably means what say you have to go to specific tools like that. The question from Aman: why reduce the harmonic distortion? If the harmonic distortion level is within the limit, then it would say that's definitely not going to have a question of way to reduce. But if the harmonic level is beyond the limit, then definitely you need to reduce this harmonic distortion. Simple reason because this has quite a lot of ill effects. When I say means it increases the current, increases the temperature, reduces the life of the equipment, means more functioning of relays. It's not one. I believe the slide, that's what it is, not probably my slide. I'm just running through the another slide. So here you can see some of the impacts or effects of harmonics like increased losses, reduced torque in rotating equipments, and even you should not tell reduced torque. Probably means this harmonics introduces braking torque as well. If it is the second harmonic in nature, then it is premature aging. That means life of the equipment comes down. Increased audible noise from rotating and static equipments, maloperation of equipment, that could be relays, etc. And probably the neutral current sums up in if it is let's say zero sequence current, etc. So that is the answer to the question why to reduce the harmonic distortion from Aman. Please explain why the voltage VHD is increased when the short circuit is reduced further. So means grid short circuit level has an impact with what to say you can see the simulation when the harmonic current is same, but means what to say when we are reducing the short circuit current, you can see the source impedance is increasing. When you are increasing the source impedance, probably means I am just comparing with the 20 kilo short circuit and 2 kilo short circuit, you can see the impedance. So the increase in impedance results in the voltage distortion at your point of coupling. That's the real reason why that is increasing the harmonics. What's the impact of harmonic sizing on the cables? That's the question from Gunasekaran. So I mean, so to say, impact of harmonics on the cable sizing is same as the impedance. So I mean, so to say, whether you are looking at the question of the impedance of the cable means below this point of coupling or the above point of coupling. So whenever you are increasing the impedance below your point of coupling, your harmonics at total harmonic distortion at the point of coupling will come down. Whereas if you are increasing the impedance at the above point of coupling, that is at the grid, then probably means your total harmonic distortion will increase. Which IEC defines it? There is no direct relationship between cable sizing and harmonics. That's an indirect effect. There is no IEC which talks about. But IEC for IEC for harmonics, I think that's clear. That's to answer a question of Gunasekaran. I think standards, I think somewhere she has made it. Yeah, this is a standard of IEC and IEEE. That's clear. And IEC standard for a cable is IEC 60502.